da 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 da. Honors Physics Lesson 3.1 Intro to Forces. Alright, so first, we talked about this earlier in the semester, and I told you we'd be coming back to it because it was very, very important, and it is. So a force is a push or a pull. We can measure it in pounds, or what we're going to be measuring in this class is newtons. Newton is a derived unit coming from mass times acceleration, so kilograms times meters per second squared. And technically, this F equals ma is his second law, good old Newton. But we'll talk a little bit more about it in the next section, which is 3.3. 3.2 we'll go through his first law, the law of inertia. But this might be helpful for a couple of your questions on your homework. Yay, homework! Just joking, no one likes homework, that bites. Alright, so a couple example of forces. We got force of gravity. Gravity always sucks. It pulls things down towards the center of whatever it is we're on. So in this case, it'd be the Earth. If you're on like Mars, it'd be the center of Mars, center of Jupiter, center of an asteroid. All good things. Alright, people can push stuff. We call this an applied force, and we're always going to want to label it F for force, and then whoever is applying it, Roy, Sally, Billy Bob, Toothless Joe, whatever. Things can also push stuff. We call that normal force. And this is important to remember because it always applies perpendicular to the surface. And I apologize if this kind of looks a little funky the way the slide is. I fixed it and saved it, and yet for some reason it's not saved. So whatever, it looks bloop, bloop, bloop. Anyways, when a normal force is applied, it's always going to be perpendicular to the surface. So one of those type of situations, which is fine if you have an object that is, sitting on a table. Normal force just goes straight up. The reason that I'm mentioning it now, because if you have an object that's not sitting on a flat surface, like let's say on a ramp, there you go, look at that awesome ramp, the normal force still goes perpendicular to the surface, whereas gravity goes straight down to the center of the Earth. Yay! That was a good movie, by the way. At least I thought it was good. Brendan Fraser. Alright, whatever happened to that guy? Anyways, so make sure to apply it, label that, whatever is applying the force. Other example of force, and this is going to be a big one here in class, is the force of friction. So if you can picture sandpaper or any uneven surface, if you were to look at a surface close enough with a microscope, even the smoothest surface would have ridges, unevenness, and that causes resistance. This resistance is the resistance of motion. Generally think of this as coming up as an energy transfer of heat. But the good thing to remember with this is friction always acts opposite in the direction the object is moving. So if the object is moving this way, then friction is going that way. If the object is moving this way, well then friction is going that way. And that's important to remember, especially when you have like a ball or a box or something going up a ramp, because as it goes up the ramp, friction is going down, which amplifies the force of gravity. But when it's sliding down the ramp, it's going up. And you'll come into that a couple times throughout this section where friction kind of changes direction based on the object's motion. And the other one is tension. So tension is a force that is applied to anything like a string, a rope, cable, wire. It's whenever forces are acting opposite of one another and kind of causes a stretch. And here are some examples right here. Pulley system. Notice there's tension here and tension there. It's also important to note that, let's say you have, let's call these boxes people. Alright, this will be Mr. Squareface, and this would be Joe. Anyway, so they're both pulling on this rope, and they're pulling on it with some force. Let's say he's pulling it with 500 newtons to the left, and he's pulling it 500 newtons to the right. The net force or the tension on the string is not zero, right? They don't cancel out, but really, if you were to able to take some kind of measuring tool and measure that force, it would be 500 newtons. That's the tension on the string. So normally tension is going to be whatever the maximum force being pulled on it is, and that's going to be in the center. Alright, so a couple things about forces. Force has nothing to do with how fast something is moving. And you can apply a really large force to something really small and make it move very, very fast. And you can apply that same large force to something that's ridiculously big and it won't move at all. So that brings me to number 2. It's possible to push something and have it not move. Even more importantly, it's possible to push something and it's moving in the other direction. Similar to the displacement, it's a vector quantity, so it's going to have direction, north, south, east, west. It can be negative, it can be positive. You want to be able to draw the force coming out of an object. So this would be pushing or pulling to the right. Right? So pushes and pulls are treated in the same way, always coming out of the center. And then here is a good picture of a free body diagram, and the free body diagram is just showing the forces on a box or object that is coming across something. So here we got normal force, force of gravity, force applied, force of friction. We always want to draw the net force outside of the free body diagram, so you don't want to include it. If you're going to draw velocity, which on some of these I ask you to, draw it either underneath or above, and label your acceleration. So velocity and acceleration are not forces, so they would not be included in a free body diagram because this only force. Alright? Also, when drawing your forces, if you have something that's sitting on an object and it's not moving up or down, that means the normal force and the force of gravity are equal. You can indicate that by these little hash marks here, but you also really don't even need to draw them. The way I like to do it in class is only draw the forces that are being applied to the problem. So yeah, there could be air resistance, there could be water, there could be something else, the weight of the atmosphere coming down on, the 14 pounds coming on this object. Yeah. That's not important to the problems. I just want to know which way is going right or left and what the net force is. This part is going to be important to the problem, not those. So if you want to include it, that's great. I'm not going to mark you down, but I'm also telling you, don't do more work than you need to. Velocity vectors, we already went over those. Just make sure you don't include it on a free body diagram. Alright, here's a cart, and we have it, and he's going to stop the cart with a force of 20 newtons. It's rolling west, so that means he has to push to the east. And then we have this awesome cow that's standing on the road, so Roy pulls the cow to the west. Alright, so if you're going to pull something to the west, it's going to go that way. So there's our awesome cow. Yay! Alright, so net force and total force. The total force of all the forces on the object is going to be the same as our net force. Basically, we're just adding all of them together to see what the total force is acting on that object. It's just the sum of all of them. That's what that little sign means. Somewhere over the rainbow. Alright, so quick practice. We got some Roy, he's pushing things to the right with 8 newtons. Sally's pushing to the left with 12. There we go. So it looks like that's our center. Here's Sally. She's pushing. Oh, no, she's pushing to the left. Oops. There we go. then here's Roy. Pushing to the right. Could you include normal force in the force of gravity? Yes, but this refrigerator is not going up and down. So I'm not going to include it just for, the sake of not doing more than we really need to. So then our sum of our force is going to equal Roy plus Sally. So 8 plus her negative 12. So the force net equals negative 4 newtons. Now again, that doesn't tell you how fast it's moving. It depends on its mass and the force of gravity, static friction, kinetic friction. But we'll get into that later on. Right now, we need to look at the net force. All right. So, box of jelly donuts sits on the table. Mr. McGuire pulls a box with 500 newtons at 30 degrees south of east. Mr. Hecker pulls it at 75 south of west. The force is 600. And then I, Mr. Hernandez, that's a fancy way of saying my name, pulls the box straight north with a force of 700 newtons. Find the net force and include a free body diagram. Alright, so for the interest of time, because I've been talking for a long time, I'm going to make this go quick. So this is like we've done in previous sections. So we're going to take this and let's see, we'll call this A, Mr. McGuire, so 500 newtons at 30 degrees south of east. We'll call this B, Mr. Hecker, 75 at 600 newtons. .5 degrees south of west, and then I am 700 newtons due north. So just like with previous problems, what you're going to want to do is you're going to set up a grid. That's a really bad grid. Under X, under Y, A, B, C. So I'm not going anywhere east or west, so that's 0, and that's 700. We'll have to take sine and cosine of that, and that should be negative 155.3 and negative 579.56. And then Mr. McGuire is going east, so this is 433.01, but 433 is fine, and negative 250 because he's going south. Make sure you include the negative signs for south and west. North and east are all positive. So we'll add those together to get our resultant components. And you should end up with an X of 277.7 and negative 129.56. Pythagorean theorem. And to get your angle, it's tangent 1, y over x. And you should get 306.5 newtons at 25 degrees south of east. Yay! And we're done. Okay, make sure you tip your waitresses and all that fun stuff. Have fun. Talk to you later. Hasta luego.